Cool, let's go. So, 1 billion biometric users of WorldCoin. And how do we use cryptography to make all of this happen in a maximally privacy-preserving way? I want to start with pointing out that us cryptographers were hoarding GPUs before it was cool. We now have this whole field of machine learning exploding, and you saw a lot of this on main stage. But the field of cryptography has had an almost as impressive boom in the past decade, where we've created a ton of new, very powerful tools that allow us to solve problems that were previously just completely unimaginable. And to show you what these tools can do and how we use those tools to verify the unique humanness of all the people who verify through an orb, without ever having any of that biometric data leave your device unencrypted and ever being revealed to anyone besides you. I'll show you how we do it. Let me take you on a user journey through signing up and using an orb-verified World ID. Yep. So it starts simple, like you've heard of the project, you go to the App Store, you download the wallet, and you open the wallet. Now a lot of things already happened at this point. The app bundle is signed, there is a certificate chain that proves that this is indeed the correct app that's been built, end-to-end encryption is established, keys are generated in the secure enclave, your World ID public key is generated, and so on. All of this is old cryptography, and I'm not going to cover that today. I'm assuming that people are familiar with these things in general. So let's get to the next point. So now you have a World ID in your wallet. You need to get this orb verified. So you open the wallet, you go to find an orb, and then you're in front of the orb, and what happens is the wallet will show a QR code. The QR code gets seen by the orb, and now an end-to-end encrypted, authenticated connection is established between your wallet and the orb. Then you and your wallet need to make sure that this is actually a genuine orb. How do we do that? You have the orb public key, and you make sure that this is in the set of known orb public keys. And this is where we meet our first fancy new tool, consensus algorithms. Decentralized consensus allow us to create public global state, like all the known and known correct or public keys. Now, what are these things? Decentralized consensus has been an open problem for a very long time. We know about distributed consensus, the stuff that runs all our databases. Paxos, Raft, you know it. The property with those is that they're not very resilient. You could not run Paxos on the public internet because they assume that participants are honest. But if you have a minority of people actively trying to maximally mess with the system, as is always the case on the public internet, these will break down. For that, you need a much stronger system. You need something called decentralized consensus. One of the areas where this has been a major blocker is actually in decentralized currencies. People have been working and trying to build these since at least Charm's work in the 80s. But the blocker has always been that there is no good, fully decentralized way to make sure that to establish a global agreement on which of two conflicting transactions should be the one that goes through. This has been the thing that's been blocking it there. What happened in 2008 with the Bitcoin white paper is that a clever solution was found. Instead of looking for a solution that gives you mathematical guarantees or cryptographic guarantees even, we slightly lowered the bar to getting economic security guarantees, meaning that an adversary needs to spend at least X amount in order to mess with the system. In this slightly weakened set of requirements, we can now solve the problem assuming we have a decentralized currency. And here's where the catch-22 comes in. You need a decentralized currency in order to get decentralized consensus and vice versa. So the two of them had to be created together, and they are intrinsically linked in sort of a symbiotic way where one allows the other to be created. The initial versions of this focused purely on building a transaction system. Since then, we've extended these to be generic trackers of public state and validators of state transitions. And this gives us the decentralized consensus algorithms like Ethereum that we know today, where you can basically create any kind of database-like structure and have it run on global infrastructure in a way that cannot possibly be messed with. It's a very powerful primitive. And we're using this to create a public, verifiable set of all the currently registered or public keys, thereby kind of replacing the more traditional centralized infrastructure of certificate chains and revocation lists and so on. So you as a user can go to the Ethereum blockchain and make sure that the orb you're currently talking to is actually a correctly audited and manufactured orb. Then you get to the next step. We'll have time for questions at the end. Then we have the orb take a selfie. So what happens is that you stand in front of the orb makes sure that you're a real live human being, not someone holding up an iPad with a picture or a deepfake or so on. It takes a high resolution picture of both of your eyes. It signs it with the public key that you just verified, and then it sends the picture to you. So now you have your picture taken in an authenticated fashion. So you have a picture that you can prove was taken through the correct processes by an orb. What you now do is you take this picture and you compute your biometric template, a thing we call the iris code. This is a machine learning algorithm that takes the raw image, applies some convolution filters, and now it becomes essentially a bit vector. And you can now do all of this on your device. But how will anyone else know that you've done this process correctly? Like maybe you modified the software to do something else. And this is where another new tool comes in, zero-knowledge proofs. This is probably the most powerful of the new tools that have been created in the last decade. And what this allows you to do is you can do a computation and then prove to anyone that you've done this computation correctly without them learning anything about it that you don't want them to learn. So you can prove that you've computed the iris codes correctly without actually revealing the iris codes to them. How does this seems impossible at first. So let me try and give you sort of an intuitive explanation of how this could even be possible. If you look at digital signatures, something we all know, what they basically are is a zero-knowledge proof that you know the private key to a public key without revealing the private key. Under the hood, these rely on some sort of hard problem, like the discrete logarithm problem. So what you're basically proving is that you know the solution to a discrete logarithm problem without revealing this solution in the process. Now imagine that instead of discrete logarithm, we use a slightly different problem, like Boolean satisfiability, where you have a certain circuit of and OR and NOT gates, and you want to prove that you know a set of bits that makes this circuit evaluate to true at the end, without revealing any of the inputs you don't want to be revealed. I hope this is not a big leap of faith to go from discrete logarithm to Boolean satisfiability, but what happened now is that Boolean satisfiability is NP complete, and in a very trivial way. Anything you could possibly want to compute we can express in terms of a potentially very large but tractable number of Boolean gates. And this is indeed what happened. This is how modern zero-knowledge proofs work. They are, you take an existing algorithm, you express it in a circuit. Now, a thing that people do in practice to improve performance is instead of taking a Boolean circuit with zeros and ones, we use something called an arithmetic circuit, where your values are large numbers in a finite field, and your operations are addition and multiplication. But the basic idea is the same. And over the past decade, we've gotten ridiculously good at doing this for very large circuits. For example, people have been able to take an entire RISC-V CPU, implement it as an arithmetic circuit, and be able to run programs in this virtual CPU and prove correct evaluation. And people have been able to run Doom inside of such a virtual zero-knowledge proven CPU, and have been able to run it at multiple megahertz of clock speed. So we're still compute constrained, but it is shocking how rapidly it is increasing what we can do in these things. Now, where do we use these? So all of what I just described, taking this image, verifying that it was signed by an orb, deriving the iris codes, we do all of this inside of such a zero-knowledge proof. And then we do one more step. Instead of having the iris code as the output, we compute something called secret shares. This is basically taking the information, splitting it up in multiple parts, encrypting it into multiple parts, such that you need all these parts to be combined in order to learn the original. I'll get into why that is useful in a moment, but what we now have is like an end-to-end thing that allows the user to take their orb image and turn it into known correct secret shares without ever revealing any of the source image or the intermediate biometric template and so on in the process. What do we do with these secret shares? These now get sent to a multi-party setup. There are a number of nodes that participate in a multi-party compute setup. Each of them receives a single secret share, and then they run a program in there that makes sure that, hey, these secret shares together represent an iris code that doesn't match any of the ones we've seen before. But how did it do that? Because each participant only has one of these secret shares, and you need all of them in order to know anything about the secret. It turns out that with multi-party computation, you can actually compute on these secret shares by talking and communicating with each other in a way that none of the parties learns anything about what they are currently computing, except for the final outcome that you want to be revealed, which in our case is a single bit, whether this human is unique or not. And the cool thing about, in particular, the MPC scheme that we're using is that it's simple enough that I can try and explain to you right here. So let's start with the basic, with a basic secret sharing scheme. Let's say I have a random, let's say I have a secret number S that I want to share with 3 people such that none of them can learn anything unless they work together. I can do that by picking 3 random numbers such that they sum to my secret value. Individually, all these numbers are indistinguishable from uniformly random. And in a sense, the secret is stored in their correlation. And you don't know the correlation if you don't have all the shares. But we want to do computations on these secret shares without anyone needing to combine them. What can we do? Well, if we have 2 secrets, and all the participants have 1 share of each secret, we can actually compute the sum already. we simply have each participant add the two shares together. And now, what they end up with is a secret share in the outcome, in the sum. We can do the same for multiplying it by a publicly known value. But how do we multiply two secret values together? This is where things get more complicated. And we do need to solve this, because in order to build arithmetic circuits, we need to be able to add and multiply secrets together. But once we have that, we can basically compute anything we want. For this, we're going to augment the way we share the secret a little bit. Instead of having 3 parties, each receiving 1 share, in a way that you need all 3 shares combined to get to the secret, we're now giving each party 2 shares. Party 1 gets share 1 and 2, party 2 gets shares 2 and 3, and party 3 gets shares 3 and 1. We're still secure. Individually, each party cannot learn anything about the secret. But we've lowered our collusion threshold, because now if any two parties combine their shares, they can learn the secret. We no longer have a threshold of 3, we have a threshold of 2. So we sacrificed a little bit. But what we get in return is that we can now multiply 2 secrets together. And the way that works is, well, if we just write out what A is in terms of secret shares and what B is in terms of secret shares, and we just expand the product and collect the terms, you'll find that the first line is something party 1 can compute, because it knows all of the coefficients that happen there. Same way, party 1 can compute the second line, and party 2 can compute the final line. So together now, they can compute this product. But each of these lines is just a number that when you add them together, you get the product that you're trying to compute. In a sense, you now have computed an additive sharing of the secret product you want to compute. And this additive sharing in itself is not enough to do a whole arithmetic circuit, because we cannot do multiplications on additive shares, but we can do a resharing. We can take these additive shares, sort of re-encrypt them, add additional randomness to them, such that they are, again, like uncorrelated with the original values. And then each party can just send one of its share to its neighbor. So party 1 sends its share to party 2, and so on. And then we find ourselves back in the replicated scenario where we started with, and we can continue doing multiplications. This is an example of a very simple linear multi-party computation protocol. There are more sophisticated protocols out there that have some performance advantages, but it gives you an idea of how these things can work in practice. Now, what do we do with that? So we now have these iris codes secret shared in a way that we can do arbitrary computation on it without anyone learning anything about it. And we run this large arithmetic circuit that matches the incoming iris code against all the ones that have been submitted before. And if there is no match, and this is a biometric template, so it's fuzzy matching, and it's actually quite involved to do this computation. If there is no match, the MPC signs off on the fact that, yes, you've just submitted a correctly computed, because they verify the zero-knowledge proof, a correctly computed biometric template that is unique, so you're a unique human being. Critical in this is that the participants in the MPC do not collude. They should, under no circumstances, get together and compute and combine the secret shares, or even compute information on it that doesn't follow the protocol. The other thing is that this MPC protocol, the one I just presented, assumes that the participants follow the protocol correctly. They cannot learn anything by sending incorrect values to the other parties, but they can mess with the outcome, and we don't want that. Now, fortunately, at this point, we already achieved our primary goal of getting privacy of the data. Now we're just trying to achieve correctness of the outcome, which is in a sense less sensitive. So we take a different approach here. The first is, of course, who are going to be running those parties and holding those shares. For that, we need reliable, neutral, credible, external parties. We found some. The second strategy we take here is trusted execution. So this is more of a traditional cryptography thing, but it's basically you can build computers in a way that they don't allow you to run any kind of software that wasn't like signed off and approved beforehand. We require that the MPC participants run all of their software in a trusted execution environment. This required some major innovations because our algorithms, because of the sheer volume involved, run on H100 GPU clusters. So we're developing technology to run entire GPU clusters inside of a trusted execution environment. And the parties verify that before they engage in any kind of protocol, that the other party is running a correct protocol. So that's where trusted execution comes in. Now, what are the allowed protocols? The parties need to know this. This is where governance comes in. And this is, again, an area where consensus algorithms are very useful. We can create a smart contract that publicly shows that these are the approved algorithms that the MPC is allowed to compute over this secret data. And then have a body make sure that indeed these algorithms preserve the user's privacy and so on. An important part of that is another, not even a cryptographic tool, but I would say an important value that comes out of the blockchain ecosystem, open source. People need to be able to verify the technology that they're using, otherwise your security guarantees don't mean much. So all of this is, of course, open source, and anyone who wants can track to the line of code which protocols can even be run on this in the first place. Now, when that whole ceremony is done and the user received the signatures from the MPC that say that, hey, you've just submitted a unique biometric template, now the user can use that to insert their public key into the set of all verified humans. Again, this set lives on Ethereum. There is a very large Merkle tree there that contains all the public keys of all the people who've successfully signed up this way. In order to add yourself in there, we use something called a snark, a succinct non-interactive argument of knowledge. It is a way to take a large computation, like inserting millions and millions of users in a large data structure, and compress it down to something that can be cryptographically verified in a tiny and finite amount of compute. It is closely related to zero-knowledge proofs, and usually the two are actually the same, and it's called a ZK snark. But we use this in the non-zero knowledge fashion to optimize our usage of the fairly limited blockchain space that is available. Now that your public key, your world ID, is part of the set of verified humans, you want to use it to claim some handout or verify that your Twitter account is associated with only, that it's your only Twitter account and so on. So how do you do that? You again create on your device a zero knowledge proof that you know the private key to a public key that is in this Merkle tree that lives on Ethereum. And in the process, the only thing that you reveal is the root hash of this Merkle tree. Everything else you keep secret. Now, anyone receiving this proof knows that you must be a verified human being. Otherwise, you could not have known a private key to a public key that is in the set. But they don't learn anything about who you are. That's step one. That's probably the most powerful layer of anonymization in the system. Then in order to use this and let's say claim something, we need to know that, well, you're anonymous, but how do I know that you're not the same anonymous person that already tried to claim it? For this, something called nullifiers are used. These are essentially context-specific random numbers that only tell that you haven't done this particular action before. So when you use World ID, for example, to create a one-person, one-vote governance process, we can guarantee that people cannot vote twice, but we wouldn't even be able to tell if this person also voted in this other election. Every single action humans do using World ID is completely disconnected from every other action that same human has done or any other human has done. It's a very strong anonymity guarantee. Then, this is just World ID or humanist verification. What I'm very excited about is the things we can do next. We now have NFC IDs being integrated, and you can imagine using a zero-knowledge proof to prove that, hey, you have a passport that proves that you're of a certain nationality, that you're not on some sort of blacklist, or as simple as you can use it to prove that you have a passport that shows that you're above 18 without revealing anything else about yourself. And you can provide these zero-knowledge proofs to third parties that need this, and they will not need to learn anything about you that they don't want to store or that you don't want to reveal. So I'm very excited about what these primitives that are relatively little known about can do once we apply them to a broader world. And I think with that, I want to end it and kind of invite you to ask any questions if you have them. Also, please read this. Thank you.
Mic test. Is this on? Great. So in two-party SMPC, there's a central supervisor or coordinator node. Is that also present in the three-party SMPC?
No. It's not even necessary in a two-party. It's just an older version of the system that we've been rolling out. We've been in the process of migrating to sort of the end state solution as I presented it here.
Cool. Thank you very much.
Thank you for the presentation. You explained us a primitive of federation control MPC. What size of this federation is expected at the scale of 10 billion humans? This is the first part of the question. And the second one, what you do with living parties and how you prevent them from building a K of N when they left.
Sorry, I couldn't hear those questions. Let me just get...
What is the size of federation of MPC nodes at the scale of 1 billion humans? And what you do with living nodes if they can collect K of N outside the left?
Gotcha, yes. So this is about what is the size of the MPC setup and what happens if people join and leave. So right now, we're still using a linear scan algorithm, which is very computationally expensive. The bandwidth between the party participants at the moment is measured in terabits per second. So this is not a very scalable solution. We're working on an MPC version of a vector database index structure such that we can scale this with logarithmic complexity. Now, at the moment, we're running on a 2 out of 3 setup. Plan is to grow this a little bit to, let's say, a 3 out of 5 setup. But I don't think, just purely because of the resource requirements of operating a node and the reliability we expect from it, that this would be something where we see tens of thousands of nodes, like you would see in, let's say, a decentralized consensus algorithm. It's also not required, or maybe not even desirable from a perspective of the kind of guarantees that we would like for the system. To get to the second part of the question, what happens if people join or leave? It's actually pretty straightforward to re-encrypt all the secret shares. So you can make this kind of a live process where if someone leaves, their secret shares will be nearly immediately obsolete and not able to be combined with any of the ones that are live currently. MPC actually has a lot of really nice security properties. It's one of the few cryptographic primitives we know that are so-called information theoretically secure, which means that we know it is impossible to break them no matter how much compute you have, even if you have a quantum computer. None of our crypto really has these properties, so that's quite unique. The other thing it has, which is really nice compared to, let's say, alternatives like fully homomorphic encryption, is that it is always forward secured. Like even if something leaks at this point, all future data will still be secured because they don't have any key material in common like you would in alternative designs.
Hello. I have a few questions. First one is in regards of the chain. Is it like basically based on Ethereum L2, right? You're gonna be posting like proofs or like batches to Ethereum, right? That's how you use Ethereum security?
Yeah. So we generally use Ethereum mainnet where we can because it has the highest security guarantees. We've just talked about World Chain, which is kind of disjunct from this system. That is what users use for the crypto wallet side of things. This system, and particularly the Merkle tree of all humans, lives on Ethereum mainnet. And this Merkle tree batcher, this snark that we use to make it efficient, in a way is a ZK rollup. So in a way we have a ZK rollup where users can add their public keys to Ethereum mainnet.
Okay, so it is a hybrid between optimistic rollup and ZK rollup, or it is only ZK rollup?
It's a hybrid. Like we use it in different ways in different places of the system. Like the protocol governance, the set of orbs. There is no reason to use a snark there. We can just use plain Ethereum there for convenience. For the insertion of all these users, and we're talking about like thousands per hour here, we use cryptographic techniques to make the process more optimized.
Okay. In regards of the sequencers or the multi-party computation, will it be ever permissionless? If no, why?
What permissions?
To become like in the multi-party computation, like to become this like party of sequencer.
Like I said, it's not interesting because it doesn't provide substantial security improvements, and it has tremendous resource requirements, which is why we picked threadable parties. But what you could do is make the governance process of how these parties are selected decentralized, and that is something, of course, we will be doing. I think this was the last question. I can take questions. I'll be here all day, so I'll take the rest of the questions offline. Thank you all.